When we're dealing with counting and probability, we often need to use combinations and use some of our counting principles in order to compute the probability, specifically because sometimes our sample sizes are going to be too large to list out the possibilities, and even our event space may sometimes be fairly large. So in this example right here, we're dealing with lotteries, and those lotteries we know have some enormous prizes if you choose a set of 6 numbers out of the first n positive integers, where n is usually between 30 and 60. So sometimes there are as few as 30, sometimes there are as few as 60 numbers to choose from for a lottery. What's the probability that a person picks the correct 6 numbers out of 40? So in this situation, we're going to establish the fact that we're going to pick 6 numbers out of those 40. Now to pick 6 numbers out of 40, we first have to think about the fact that these 6 numbers need to all be different. There's no sense in trying to pick the same number more than once, because at that point you would lose, because they're not going to actually choose from a number that's already been selected for one of these. So of course one of these sequences could be 1, 3, 27, 12, 39, and 16. And this would be one possible sequence. But there are too many of them to list out. So our sample space is the set of all 6 numbers, consisting of values from the interval 0 up to, or rather 1 up to 40. So 1, 2, 3, 4, 5, 6, all the way up to 40. So because these numbers can't be repeated, we know that a combination would be useful in this case. So the size of the sample space is the number of ways that from the set of 40 numbers, we could choose 6 of them. And this turns out to be a fairly large number. This is 3838380. Now the event is to pick, is the set of all winning numbers. Six numbers. Well, in each lottery, there's only going to be one set of 6 numbers that causes you to win. And we're assuming that you can't have these in different orders, that you just have to pick the 6 numbers that are selected by the lottery machine. And so the size of this event space is going to be 1. There's only one correct ticket. And the probability of getting that event is going to be the number of ways in which that event can occur divided by the size of that sample space. So there's only one winning ticket out of 3,838,380, which comes out to about 0.000000026, which that number is 0.00026%. So the very small likelihood that you win, and that's probably one of the reasons why most people don't win, is because there's such a small probability of picking the winning number. Now, other situations where we might have to count, let's say we're building a hiring committee. It's going to consist of 5 people, and it's going to be formed from 8 females and 9 males. What's the probability that we get 3 members that are female and 2 that are male? Well, in this case, we have to consider the fact that if we look at these 5 people, the order in which they're drawn doesn't matter. So whether we pick a female and then a male and then female and then female and then male, that is definitely an outcome where we would have the desired event, which is to get 5 people where 3 members are female and 2 are male. So the first thing to think about is S, which is the set of all possible 5-member groups. Okay, now the event that we want to occur is to get 3 that are female and 2 that are male. But if this is going to be done somewhat at random or in some sort of random fashion, then the number of ways in which that could occur is to say from the 17 people, so we have the 8 plus 9, from those 17 people, we're going to select 5. So that's really just 17 combination 5. and that comes out to 6,188 possible 5-member groups that we could form out of 17 people. Again, no repetitions are allowed. The order in which these happen is not specifically of importance. So we now need to look at the event space. So the event space is the outcomes, the set of all possible I'll just write it like this, 3 female and 2 male groups that we can create. So the first thing we need to figure out is if we have 5 slots, and into those 5 slots, we want to fit 3 females. That means that from the set of all females, which we know there to be 8, from 8 females, we want to select 3 of them. And this is going to tell me the number of ways in which I could select 3 females from a group of 8. For the males, we're going to want to know from the group of 9 males, how many ways are there to select 2. So Joe, Tom, Tom, Joe is going to be treated as the same because that's the same 2 members on that committee. These come out to 56 and 36. So that means there are 56 different groups that you could create out of the 8 females, choosing 3 of them, and there are 36 different groups that you could create by having 9 males and choosing only 2 of them. Now, each of these 56 groups has to be paired with each of these 36. So that means that, for example, one possibility here would be to get, I don't know, we'll just say Joe, Tom, or I guess this would be our females, Jenny, Tiffany, and Leanna. And then from there, we need to pair that group with all the different 36, 1, 2, 3, all the different 36 different groups of 2 males that we might have. So maybe this is Bill and David, maybe this is Bill and Frank, and so on and so forth. So what we need in order to get the size of E is to figure out the number of different groups we could create with those 3 females and those 2 males. And that would be 56 times 36, because again, we're going to have all of these different branches down here that are going to pair with all 36 male groups, and there are going to be 56 separate branches of corresponding to groups of 3 females. So 56 times 36 is the size of our event space, and we want to find the probability of this event. So we're going to take the number of elements in E divided by the number of elements in S. The number of elements in E, just to write it as a formula involving these combinations, 8 choose 3 times 9 choose 2 divided by 17 choose 5. And we know that this is going to be 56 times 36 over 6,188, about 33%. So what we can conclude is that if we were to many times do this, of course, because as we described probability, 33% doesn't really mean a whole lot when you're doing something once. We're going to form this committee once. But if we were to randomly draw people from a hat to form this committee, there would be a 33% chance, or 33% of all those committees that we formed would consist of 3 males and 2 females. So, or 3 females and 2 males. So this is a way in which we can use our counting techniques in order to address probability problems.